These are really ancient curves that have come to be real important in modern mathematics too. These are not good. And the reason I put this thing in, hold on. All right, hopefully you can. I hope. I was just saying these conic sections they go back to antiquity. The ancient Greeks did a lot with these, and we still use them quite a lot today. You'd be amazed how much these come up in mathematics. Plus, they're sort of the next simplest group of things after lines and planes, flat things. After that, the next most interesting or basic thing is conic sections. Here's where it comes from. Remember the Greeks, when they did their plane geometry, they did it with just a compass and straight edge. They proved their things with a compass and straight edge, and so they'd get this compass and they'd make a circle, and then they get the straight edge and put it down, and they'd prove all sorts of things. And Euclid's 7-volume work, The Elements, it's called, on Euclidean geometry was uh, the most popular math book ever, and the second most published book after the Bible until recent years. I'm not sure if it's still that case or not, but Euclid's Elements had lots of proofs involving these things, uh, involving a compass and a straight edge. And then, if you think about it, you can then do some three-dimensional things. And this goes back to Apollonius, another ancient Greek, who endeavored to prove lots of things in this regard. Suppose now you take 2 points, and in Euclidean geometry, one of his axioms is that 2 distinct points determine a unique line. But now you take in 3 space and you rotate this point in a circle holding the other one fixed. What do you get? If you rotate the line holding this point fixed and rotating this point in a circle, it sweeps out what we call a cone, right? So there's a cone gotten by lines and circles using 3 space. Now, what happens if you decide to cut this cone with something else? You could take a line here over this way, and this time let's move both these points straight along. Maybe let's move them this direction, and we sweep out what's called a plane, right? If both points move together. And we use this plane to cut the cone horizontally. And what would we get if this is a circle up here? This is a circle down here, right? So the cross section of the cone intersecting with a horizontal plane is a circle. Next time maybe I'll put it up, but you might in the meantime look on Wikipedia or any other favorite source. You can look on probably some of these websites like Purple Math or the other math websites. If you Google Wikipedia conic sections or conics, you'll find lots of great pictures on here. I'll try and put those up next time. Now you say, suppose I take that plane and I intersect it at a little bit of an angle here. I'll just tilt it a little like that. Now what does it look like an intersection? It's not a circle anymore, but it's just tilted a little, makes an oval shape, right, is what I was looking for. And this oval shape is something you've probably heard of before called an ellipse, all right? Maybe you saw some of these in trigonometry. Anybody see these curves in trigonometry? Sometimes they have a little time at the end they do these. No? Did? Yeah, some of you did? Okay, good. Now, suppose you tilt that further until it's parallel to this edge here, and I take the plane and run it right down like that. Now it intersects in this kind of a curve that doesn't close because it's parallel to the edge. What is it now? Anybody remember that one? This conic section is a parabola. So by cutting a cone with a plane, we can get all these different important conic sections. Now if you cut it even at a steeper angle, maybe like this, you can even make it vertical. Now it cuts both halves of the cone, right, the top and the bottom. And each one gets cut in a curve that looks something like this. What's that called, do you think? Those of you that saw some of this before. That one's called a hyperbola. Those are the four conic sections: one, circle, ellipse, parabola, and hyperbola. And they turn out to have nice, easy algebraic equations. What happened was later, people like Descartes came along and started saying, wait a minute, we can prove a lot more stuff in geometry if we just introduce coordinates instead of having to do everything with a compass and straight edge. And that immensely improved algebra because now we could prove things with equations and algebra, right? Instead of just, pictures and trying to draw the things and prove them with, just instruments. So these are the four conic sections, and then there's some other ways you can intersect it too. Some degenerate cases, we call them. Like you could run a vertical plane right through the point right here, and you get a pair of intersecting lines, right? You could also run it right through just this one point and get a point. You could also run it just right down this edge and get a single line. And there's a couple other cases that you can't really picture by cutting the cone here, but there's you can get parallel lines, or you can get no solution. So I'll put these in parentheses. Parallel lines, no solution. Because it turns out there's a nice equation to describe all these things up here, and when you put that equation down, it also has these two cases, parallel lines and no solutions. And so all these down here, because of the equation, are called degenerate cases. And amazingly, the equation is just sort of the next simplest thing in algebra after the equations of lines. So this is, and then on top of it, has all sorts of great applications. Any questions on that so far? All right. So that's conic sections developed through geometry. What we want to do is now develop them with equations, analytic geometry, with coordinates. It's analytic geometry. And they have these alternative derivations to come up with the same figures. We can do this kind of geometric figure. We could take one. This is the easiest one. You've seen this before. Everybody has. If you take sometimes they call it the locus, just means the set of all points in the plane. By the way, these are all plane curves. Why are they all plane curves? We intersected the cone with a plane. It's the intersection within that plane. So these are all plane curves. The locus of all points in the plane at a given distance r greater than 0, called the radius. from a given point, x0, y0, let's say, called the center, is called what? This is an easy one, actually. What has a radius and a center? It's a circle, right? That's what a circle is. It's all points at a given distance from a given point, right? That's what a compass sweeps out. See if I've got my thing here. So there's my center, right? And I just wrap this thing at a fixed distance. Uh-oh. I can draw a nice circle, right? I can hold this board still. There we go. All right, so everybody knows that one. But now you change that up just a little bit, and let me write the equation for it too. What's the equation for a circle then? You can derive it quite easily. The standard equation. You need to know this if you don't remember it. How would I write an equation? Well, according to the formula, it's distance, which is square root of x minus x naught squared plus y minus y naught squared, right? This is the distance formula. Euclidean distance in the plane is done this way. It's the Pythagorean theorem. That distance must be equal to the constant r. So that defines a circle with center x0, y0. It's all points x, y satisfying this of the circle, right? But we don't leave it like that. What's the standard equation for the circle? You just square both sides, right? When you square both sides, you got x minus x0 squared plus y minus y0 squared equals r squared. And this is the standard equation for a circle. It just says distance equals r, right? So that's why that's the standard equation for a circle. Whenever you see that, recognize it's a circle and be able to plot it immediately, right? I don't think the homework has any problems on that because they sort of consider that elementary, but I'll do one example just for fun. The circle at 2 minus 1 of radius 3 is or has equation, right? X minus 2 squared plus y minus a minus 1 is plus 1 squared equals 3 squared. There's the equation for the circle of radius 3 at 2 minus 1. One of the big reasons I introduced the circle, even though you've seen it all before, is now we can do the ellipse. So number 2 is the ellipse. Has just a little twist on that. Is the set of all points x, y, such that the sum of the distances from two fixed points, called foci, the center of the circle can also be called the focus. But if you want, the ellipse is all points x, y, such that the sum of the distances from a given point, from two given points, excuse me, is called the foci. Plural of focus, is a given number more than the distance between them. I'll leave that part out. Otherwise, you get the empty set or a degenerate case. Is a given number, let's say 2a. That'll be an ellipse. You give me two foci and a distance 2a, and here's how the ellipse works. Right, here's my two foci, and I plug them in like this. And now I take my pen, and this string keeps a fixed distance, right? Always this distance plus this distance is the same, and that's the definition there. You want the sum of those two distances to be the same. Let me put these a little closer together. So now I draw this kind of an oval shape. Pull it around. There we go. Pretty good ellipse, huh? So there's the foci. And amazingly, this thing turns out to be extremely useful. They had a World War II fighter plane that had an elliptical wing, for instance. But you ever seen a game called Elliptipool? They put a pocket at one of the foci, and then they put a spot on the table where if you shoot your ball over the other spot, right? Here's your billiard ball rolling over this focus. If you hit it without spin so that it bounces off the end here with angle of incidence equals angle of reflection, like in physics, right? If there's no spin, it'll do that. It'll always go right in the pocket here. So it's got that property that it refocuses anything coming from this focus to bounce off and go to this focus. And so you can always scratch, I guess you'd call it, by putting it over the spot here with no spin. But that's elliptipool. But moreover, if you go down to some of these science museums, you'll see something called a whispering gallery, and they'll put an elliptical room, and someone will sit in this seat and someone will sit in this seat. And this person will whisper as quiet as can be, and all the sound waves are reflected over here, and this person can hear it just like they were sitting right next to them, while someone sitting halfway in between can't hear a thing. Because it's not refocused here, it's all refocused here. All this bounces off the wall and comes back, as long as the walls bounce the sound back. So that's a whispering gallery. And there are other things, but you can see this has lots of neat properties. Another neat property, I don't know if you've seen telescopes or not. When I was in college, put a telescope together, and it was one of these Newtonian telescopes where you have a big opening and this long tube. It's got a little lens out the side to watch the image. Well, how does the light go down here and get to that little lens? It bounces off a big primary mirror here, is focused to a point up here. But before it gets there, it's intercepted by a little flat mirror at an angle and refocused here. And then this lens focuses on the image that's created by the big primary mirror here. And the ratio of the focal length of the big mirror to your little lens gives you your power of the telescope. So if it's 400 times the focal length of the little lens, then you get 400 power telescope is how that works. But the principle here, this little diagonal mirror here, in order that when it's tilted, give the appearance of a circle, right? This is coming off in a circle. It has to be an ellipse. If you take a circle and turn it at an angle, or an ellipse and turn it at an angle, if you turn an ellipse at an angle, you can make it look like a circle, or turn a circle at an angle, making an ellipse. And so they give you a little elliptical flat mirror here. This is a side view, right? It looks like this, and it tilts over till it looks like a circle to the mirror at the back. So there's lots of neat applications like that. In planetary physics, anybody doing that, they often, it's because it's somewhat understood, model planets as ellipsoids, which means they have, you'll see this if you go on and continue this course to Calculus 3, they have elliptical cross sections. They're like a sphere except flattened a little, so that the cross sections, instead of being circles or ellipses, you get an ellipse like this for the equator, an ellipse around here, and an ellipse the other way, around this way. That's an ellipsoid, and so those are real popular in planetary modeling. If you do your GPS units, latitude and longitude, the Earth is treated as ellipsoid with a circular cross-section this way, but it's a little flatter at the pole, just a little, enough that it makes a difference in GPS, and it's not accurate unless you flatten the poles a little, making an approximate ellipse. Then they add terrain on top of that. But your latitude and longitude is computed purely from that ellipsoidal Earth model. They've got a World Geodetic System, WGS. 84 was the first big deal one. They've been made some others since, but this one's still in a lot of use. 1984 World Geodetic System ellipse. We used that at Vandenberg Air Force Base when I worked there many years ago for flight modeling of the missiles and all that. So the point is, ellipses are in a whole lot of use, and you see them everywhere without realizing it. For instance, your lampshade at home, right? You've got a light bulb in here. What happens when the light comes out the top? It makes a cone, right? If you tilt your lampshade just a little bit, if you leave it alone, it'll make a circle. If you tilt it just a little bit, it'll make an ellipse. So they're actually everywhere coming out from these cone kind of things. You don't even think about it, but there'll be an ellipse on your ceiling if it's tilted just a little. All right, so that's an ellipse. But now we need the equation for ellipse. If this is the definition, how are we going to make an equation for an ellipse? Same way, of course, right? So we want the sum of two distances equal to ellipse. Let's put the center of the ellipse, right? It's kind of an oval shape that's symmetric at the origin for simplicity. Then, by definition, for foci, they have to be equidistant on each side to have the center at the origin. So the foci will be C0 and minus C0 for some positive number C. We have, by definition, right, the foci are part of the definition. I guess I should draw it. Right, the ellipse is this oval shape like we had, and this distance d1 and this distance d2 has d1 plus d2 equals the given number 2a. Well, what's d1? If this is the point minus c0 and this is the point c0 along the x-axis, that should look a little better. I drew it kind of crooked, didn't I? Looks like something, I don't know. And this is the point xy. Then what you have is the distance between these by the distance formula is square root of x plus c squared plus y minus 0 squared. That's the distance here, right? It's just Pythagorean theorem. Plus this distance here, square root of x minus c squared plus y squared equals the given number 2a. All right, so there's an equation for ellipse, but just like the circle, it's messy. That's why I did the circle, so you get motivation from here. If you do a whole bunch of algebra, it's not worth it. It's a lot of algebra. I'll say, I think this is in the text. I'll put C text question mark. It's at least online. You can find it. You work through a whole bunch of calisthenics like we did with the circle, but longer. You have to do square twice and combine a bunch of terms. This becomes, by separating the square roots and squaring and a bunch of algebra, the following standard equation for the ellipse oriented this way. All points x, y that have this property, the sum of the distances 2a, satisfy this equation, x over a squared plus y over b squared equals 1. A lot of books like to not put this in the parentheses. They say it this way. I like this way better. Do it whichever way you want. X squared over a squared plus y squared over b squared equals 1. The book has kind of a nice way of doing it, putting it this way, because you see what this is? This is the circle at the origin with x scaled by a and y scaled by b. So now if x is a times as great then and b is y times as great as the unit circle, then you satisfy the equation. So it tells you that you've just stretched the unit circle to be a times as long in the x direction and b times as long in the y direction. So it now goes through this point A0 and 0b, and its center is at 0, 0 here. And it also goes through 0 minus b. I should have brought some extra pins. The ones here are not good today. And this point here, minus A0. So it goes through those 4 vertices. And the homework, they ask you for the focal vertices. They mean these 2 vertices here on the focal axis, right? When they ask you for that. But when you work through these equations, you get this. And where did b come from? A is the number I told you where this is equal to 2a. But what's b? It's related to a, which was given, and c, which was given by this equation. Looks like the Pythagorean theorem, except a is on the left. A squared equals b squared plus c squared. So the b is the square root of a squared minus c squared is what it is. The thing to memorize for this is not all those deriving equations, but this standard equation for an ellipse. We'll call that number 1. I'll assume you remember the circle. And this can be 1a, the equation relating a, b in the equation for ellipse, and c, the focal distance. All right, so that'll be our standard equation for ellipse. And then suppose you don't want the center at the origin. How do you put it somewhere else? I know you know this. Any equation in a plane, right? If you want to move it somewhere else in the plane but keep it the same shape, what do? I need my guy over here to answer questions today. You just replace x by x minus a and y by y minus b, right? Or x by x minus x0 and y by y minus y0. So similarly, just by general geometry knowledge, if you put the same equation, x over a squared plus y over b squared equals 1, and I forgot to, well, no, let me point out on here, I didn't draw on this. This goes from 0, 0 to a0. What that means is that a turns out to be half the long distance across the ellipse. We call a the length of the semi-major axis. This is semi-major axis the long way, semi-minor axis this way. So a is the semi-major axis length, and b is then the semi-minor axis length, just to add that to your picture. So that was the standard equation at the origin. If you want to move it, you just replace x by x minus x0 and y by y minus y0, and x just has to be x0 units bigger and y0 units bigger, and it satisfies the same, and it satisfies the equation. So it gives you exactly the same ellipse centered at x0, y0. You go out a units over here, so it's x0 plus a, and y0 units up, y0. And so that'll be the one vertex, for instance. And you just get the ellipse over here in the same shape. This will still be a, right? This will still be b, all that stuff. And this one up here goes up b units from the center, so it's x0, y0 plus b. All right? So this equation gives you semi-major axis length a, semi-minor axis length b, and center x0, y0. Some of the problems are write down the equation of the ellipse given these properties. Right? Let me do an actual problem here then. Guess I can erase this, can I? Hopefully. All right. How about this? Find the vertices and the foci of this ellipse x minus 2 over 3 squared plus y over 4 squared equals 1. All right? That's equation 1 with a shift, right? also called a translation. So let's say this is 1 translated. To have center at whatever is subtracted here, 2, the number that's subtracted, not added, 0. Right, because x has to be 2 units bigger to square the same number. 1 translated to have center at 2, 0. So I recommend always finding the center first. It's just whatever's subtracted in here. And you notice that A, it's under the bigger number. I should have pointed out the semi-major axis, the one with the foci on it, was under X before. What happens if the bigger number goes under Y? Not only did I translate the center, but now the foci are going to be in the Y direction because the bigger number is under Y. So A is the square root of 4. A is 4, the number under Y, and B is 3. And because I interchanged X and Y in the equation, the foci are vertical. So those are the two things you can have happen. Is if the bigger number is under Y, then it's the long axis is up and down, and whatever you subtract in here is the shift or the translation. So I can sketch this thing rather easily, and actually, for answering these questions like where are the foci and the vertices, I actually think it's easier, almost easier to draw it. So I'm going to draw it. I'm going to say, wait a minute, I know how to draw this. The center, we said, is at 2, 0 just by inspection, right? What's subtracted from X, what's subtracted from Y. The semi-major axis is 4 units going up and down. 1, 2, 3, 4. So it goes up to here. And then it goes down 4. 1, 2, 3, 4. Now you can compute these, or you can just look at it and say, I know what the vertex, the focal vertices are. This one is 4 units above the center, so it's just 2, 4, right? This one is 4 units below, so it's just 2 minus 4. Once you see that visually, you just say, oh, just, add to the y coordinate in both of these. All right, that one look all right. Then the semi-minor axis is 3, so I have to go 3 units, 1, 2, 3 here to minus 1. And there's a vertex at the end of the minor axis, and 3 to the right, 1, 2, 3 here, 5, 0. So I can label all these things 5, 0, minus 1, 0. I can figure them out just from the picture. And there's my ellipse. Let's draw it with this one, I guess. Like that. And I immediately get the vertices. All right. Now what about the foci? To compute the foci, I use that relationship between A, B, and C. A and B just come out of the equation, right? Here's A, here's B. Now, A squared by 1A, I guess I could call it. A squared equals B squared plus C squared. Says 4 squared equals 3 squared plus C squared. All right. So evidently, C squared is equal to 7. C must be square root 7. We always take C to be positive. It's the focal length. So now where are the foci? They're along the semi-major axis, just up and down from the center, square root 7 units. So one of the foci is somewhere up here, is 2 square root 7. And the other one is down square root 7 units, is 2 minus square root 7. So there's the foci. I can circle those. That's how easy it is to figure that stuff. Once you have the equation and of the ellipse, and remember there's A squared equals B squared plus C squared, it's pretty easy. Okay. All right, so that's ellipses. Hang on there. We can do one more here because there's another kind of problem here. Find the equation we want to do also. So we'll go the other direction. That's given the equation. Find properties of the ellipse. What if you're given properties? How can you find the equation, right? You just remember those equations 1 and 1a. Find the ellipse, meaning the equation thereof. With foci plus or minus 16, 0, and focal vertices plus or minus 34, 0. What I recommend doing on these things? Go for the center first, I think. Where's the center? It's halfway between the foci or halfway between the vertices, either one. So we already know it's at 0, 0. But we can do it this way. Center is the average of the two foci coordinates or the two vertices coordinates. We'll just take 16 plus minus 16, the two x coordinates, over 2, and the two y coordinates, 0 plus 0 over 2. For the two foci, we average the x's, we average the y's, and we just get 0, 0, right? The point halfway between, right? You don't even have to compute this one. But there's the center. Now, what letters do we know? From the center to the vertices is A, right? So this one now tells me A equals 34, the distance from the center to either of the vertices. The distance from the center to the foci tells you C. Evidently, C equals 16. From A and C, I can find B, right? By equation 1a, I know that B is equal to square root A squared minus C squared, right? A squared equals B squared plus C squared. Solve for B, just like the Pythagorean theorem. Works like this. So it's square root of 34 squared minus 16 squared. I've forgotten 34 squared here. I should get my calculator. 1156 minus 256 is 900. Square root is 30, right? So evidently B is equal to 30. Now I have immediately the equation for the ellipse. So what is it? By equation 1, this is an ellipse at the center, so we don't even have to shift it. We just write x over a squared plus y over b squared equals 1. If it was shifted, I have to put x minus x naught, y minus y naught in here. But we already know and then it's horizontal foci just by, right, because they go left and right. That means A goes under x. If it's vertical foci, the bigger number goes under y. If it's horizontal foci, the bigger number goes under x. So A goes under x rather than y, like in the last example. So A was 34. I get that one. And B was 30. And just like that, my equation ellipse pops right out. Right? So that's what some of the homework is. Not too bad, I think. Well, the next one is the hyperbola, right? We'll have to mostly do this one next time. Hyperbola has this thing, this geometric way of describing it. Other than saying cutting a cone, you can also describe it as this is all xy, all points xy, such that the difference of the distances from two given points called foci is a constant. See how similar these are? That makes it easier to remember. Such that the difference in distances from two given points called foci is a given number. Big enough that you actually have a solution, right? It has to be bigger than the distance between the points. That'll be a hyperbola definition from the coordinate point of view. If you write that equation down, let's not write it again, but you just write the same distance equation for a hyperbola at the center. Maybe I should just develop it, but a hyperbola at 0, 0. This means you get this kind of, with foci along the x-axis, just like we tried with the ellipse, plus or minus c0. We have this equation. Here's the distance formula. Distance, I guess I better draw the picture. So the center's at 0, 0. Here's C0, one focus. Here's C minus C0, another focus. And the idea is that you take this point xy on the hyperbola if this distance minus this distance is a given number. Right? The difference in the distance has to be given. And so what you get is a curve that looks like this. Oops. There we go. And this, because you can take this distance minus this one too, and you get two what are called branches of the hyperbola. And it turns out, we can prove it with calculus actually. I don't think we'll do it in here, it's not worth our time, but they approach two asymptotes, two lines like that. And so you get a curve like that. But the picture then is that you want all points x, y such that this distance d1 minus this distance d2 is a given number. So you're going to take d1 minus d2 equals some number. I've forgotten if it's 2a or not number. And so it's x if this is at C0, here you can put it as x minus c squared plus y squared, just by the Pythagorean theorem, right? The x distance is x minus c, and the y distance is y, and so this squared plus this squared makes a little triangle here. That's that distance plus a minus square root of x plus c squared plus y squared when you're going from the other one equals a given number. Determines the ellipse. This would be doing the ones on this branch, I guess. But you apply a bunch of algebra and you get this equation, which I think I'm going to have to quit with, unfortunately. Yeah. It leads to this standard equation for the hyperbola, center at the origin of foci at plus or minus C0. X over A. This is what's really nice, too. These are very similar. Squared, y over b squared, and 1. How does that look different from the ellipse? It doesn't yet. All you put is a minus instead of a plus, and now you get a hyperbola, amazingly. How about that? Where there is one other difference, it turns out the focal distance C and A and B are related like this. This time it is the Pythagorean theorem. C squared on the left this time equals A squared plus B squared. You notice that in the hyperbola, C is bigger than A. This is actually the point here, A0, and this is the point minus A0. And B comes in the asymptotes. We'll have to do that next time. take a look at some of those homework problems. You can probably do the first few of them already. So, but we'll get to this some more.